welcome dear students. We are discussing the quantum technology, and in this quantum technology series we are discussing the quantum sensor. So we have discussed the many sensors, but what are the properties of the sensor? That is very important part. So in this section we will discuss the important sensor properties which is required for the quantum sensing. So what are the features which is required for the sensors? So first is the bandwidth. So a typical sensor frequency response is SF, that is defined by S0 1 plus 2 pi ft2 square root 1 minus 1 by 2, with the bandwidth being B is equal to 2 pi T2 inverse. So at the frequency above the B, the measurement SNR degrades. Signal noise ratio will degrade. A common misconception is that feedback can enhance the bandwidth, but the gain enhancement at the high frequency is generally compensated by an increase in the effective noise level. So we can note that since bandwidth and the sensitivity are oppositely related to the T2, so desirable improvement in sensitivity by reducing decoherence also degrade the bandwidth. So in this context, the use of squeezing technology, or we can use the valuable to increase the values, we can increase the bandwidth without the usual degradation of the signal noise ratio at the high frequency. So another important feature is the dynamic range. So most sensors exhibit saturation when the sensed field becomes too large. So the dynamic range is typically the ratio of the target field detectable without saturation to the smallest detectable field. So again, there is generally an inverse relationship between the dynamic range and the decoherence. So that improvement T2 does not necessarily improve the dynamic range. Dynamic range is that range up to which we are calculating the value. So feedback is often helpful for increasing the dynamic range of the sensor. Another point which is very important is the scale factor linearity as well as the stability. So for sensor like magnetometers and RF receivers, the primary goal is the sensitivity. So the and the ability of the sensor to make an absolute field strength or calibrated measurement is less often exploited. So in contrast, the inertial sensors must not only have the high sensitivity but also have the stable as well as have the linear response. In principle, a model based corrections can be compensate for a non-linear scale factor but could introduce long term stability concerns. Means we are having the scale factor stability that plays a particularly important role in the sensor array in order to achieve a large common mode rejection ratio. Inclusion of the calibration field and the field gradient can mitigate the scale factor and the offset that drifts, but clearly the system stability is a key property. So system stability is the important part in the sensing properties. Another is the size, weight and the power. So that is also SWAP, that is also mentioned on the each sensor, that is a size, weight and power, that basically just prepared by the use of its application. So a dedicated sensor is often optimized for operation as a unit and may make desirable traits to accommodate a practical implementation. So the optimization of the system benefits from focusing on the long pole in the tent, like where the adjustment in the dominant contributors provide the largest gain in the modifying the unit, means that can be used or the modified in the any device. So, while further SWVP reductions may be possible, the cost of doing as so may play a role, because it leading the SWAP-C as a overall consideration. So, the cost is also the another point, so that as the size reduce, the cost is also considered. So, subscribing to rigid SWP's matrices can be misleading. For instance, creative evaluation criteria such as volume defined through the water displacement provided less practical value than considering the envelope created by a regular. So, parallelepiped, in addition, we can use the steady state power draw of the internal thermal regulation varies significantly depending on the external temperature. So, similarly, instantaneous power can exceed the steady state for the short period of the time, that is the turn of pulse operation. So, a single value may not accurately describe the need for the operation as a unit. Another feature is the orientation dependence. Sensor of a vector quantities come in a variety of the measurement configuration. So, scalar sensors measure the magnitude of the vector, whereas the vector sensor measures one or more component of the vector. So, scalar measurement should remain invariant under changes in the sensor orientation. So, depending on the configuration, they generally suffer from the dead zone directions in space where the sensor loses its sensitivity. So, both the scalar and vector measurement are subject to heading errors. So, a variation of the scale factor and the offset with the orientation of the device. So, the manifestation of the dead zone and the sources of heading errors vary depending on the sensor type, but are always crucial to study and understand. So, several schemes exist to produce the vector measurement from the scalar sensor and vice versa. So, these can be implemented with the external field modulation, spatial arrow and the other symmetric braking techniques. So, on the potential overlooked point, worth emphasizing is that scalar sensors operating in a finite field are blind to the small changes transfers to the principal direction of the field. So, these sensors are most sensitive to the variation that lightens or contract the magnitude of the vector. Another feature is the power cycling. So, sensor operating outside the laboratory are often disconnected from a power source for some period of the time. So, power cycle is important in the sensor. So, a rapid startup time can be highly desirable to achieve the internal thermal equilibrium associated with the operation. So, in addition, the active vacuum pumps such as ion pump cannot operate without the power. So, a sufficient vacuum to perform a restart should be maintained through power interruptions. So, reduction of the noticeable changes in the sensor performance such as the retrace, the fractional frequency shift in the clock from power cycling is also the desired. So, these are the desired features or characteristics of the quantum sensors. So, on the basis of that, the quantum sensors are prepared. Now, the quantum sensors use cases, we will discuss what are the applications of the quantum sensors and how they are using in the various field. So, quantum sensors basically what we have the various application in the various field, and the first we just discuss about the squid, that squid which detects the magnetic field. So, a very low magnetic field can be detected through the squid sensor. So, we discussed some specific application of the quantum sensing and its uses. So, first is the magnetic field sensing. quantum sensor can detect and measure the magnetic field with unprecedented sensitivity and the accuracy. So, application includes geologically to map the Earth's magnetic field. Nowadays, it is very easy to just to find out the geology to map the Earth magnetic field. Another is the medical diagnostic, identify and diagnose the diseases that affects the magnetic properties of the cell. You all know about the NMR and the various diagnoses we can do through the through this magnetic field. So, real life example we can take, like for example, we have the European Space Agency SWAN mission uses the 3 satellites equipped with the magnetometers to create a detailed map of Earth's magnetic field, which has application in the geology, climate research and the navigation. Another is a medicinal application. The quantum sensing developed the new diagnostic tools for a variety of the medical application that include the medical diagnosis. Means biomedical research we use for the various recording the brain activity and wearable sensor helmets. So, neural circuits, rapid clinical testing with the magnetometry of a single neuron. So, cell development and endogenous means we are having the heat generation that will be used, and that can, if we talk about the real time application of this metabolomics studies, then we are having example researcher at the University of Sussex has developed a quantum sensor that can detect the changes in the magnetic properties of the cancer cells, which could lead to the new diagnostic tool for the cancer detection and the treatment. So, you can see there are the various we are having various cells that can be detected through this magnetosensors, and very minute one neuron we can detect through this quantum sensors. Another is the temperature sensing. If we talk about the temperature sensing, so quantum sensor measure the temperature with the high precision and accuracy. Temperature sensing is essential for the material science to study the properties of the materials at extreme temperature. Moreover, the medical diagnostic to monitor the body temperature in the real time. So, in the real time directly the one can measure the body temperature through this quantum sensor. Another is the imaging. So, quantum sensors can create the high resolution images with the unprecedented detail. Like for example, a group of researchers from the USA and the UK applied the classical and quantum illumination to create the images of biological samples, and in this case one sitting and one sleeping cat. So, as we see that the researcher has observed the recumbent cat that is lightened at quantum sensor in the all conditions as opposed to the sitting cat that is illuminated with the classical approach. Now, we can see there is a difference that can be detected through the quantum sensor, that easily a great resolution you can find out in the quantum sensor. Another is an important application in the navigation. So, quantum sensors can provide highly accurate navigation, and the positioning navigation is essential for the autonomous vehicles to improve the navigation and avoid collisions, aerospace to improve the satellite navigations and the guidance system. Real time example we all have that, for example, the researcher at the University of Colorado that have developed a chip scale atomic clock. That chip scale atomic clock that can be used to improve the GPS navigation in the area where GPS signals are weak or unavailable, such as indoor or in the urban canyons. So, another application in the defense. So, if we talk about the defense, so quantum sensors have already been tested by the defense companies and militaries around the world. So, some potential application in the defense and national security includes the detecting the submarines or the other hidden targets using the magnetic or the acoustic sensing, identifying the explosives or other hazardous materials using the chemical sensing. So, we are having various chemical sensors that can find out the hidden hazardous or hidden RDX or hidden, that is very sensitive, that is why it can detect easily. So, for example, the US military signed a contract with the quantum sensor firm to improve the navigation systems and complement the global positioning system, that is the GPS. Like also there are the defense companies that mentions the military that expected to adopt the quantum sensor technology in the 2 Air Force sensors will become the cheaper and smaller in the past future. So, another application is the material science. So, quantum sensors contribute to the studies in the material science by studying the properties of the materials at the atomic and subatomic levels. So, if we talk about the real time example, then there is a National Institute of Standards and Technology then have developed a quantum sensor. So, this sensor can measure the magnetic properties of individual atoms and could have application in the development of new materials and the electronics. Means we can develop the various electronic devices by using this sensors, and also these sensors can be applied to understanding the complicated phenomena in the natural sciences. So, there is a physicist that combines the quantum sensor in the 2D crystal state, that these sensors might detect the signal from the dark matter, which is mysterious substances. So, the work is going on at this. So, another is the chemical sensing. So, quantum sensors can identify the chemicals with the high sensitivity and the specificity. So, we can have the chemical sensing that can help the environmental monitoring to detect the traces and amount of the pollutants or the toxins in the air and the water. So, medical diagnostics to detect the diseases based upon the chemical properties of the cell. So, for example, in the MIT, researchers have developed a quantum sensor that can detect the trace amounts of the molecules in the air. So, which could have the application in the environmental monitoring and the public health. So, QIS has already exhibited utility in both the communication and the computation, and the applications are expected to increase in the area such as the quantum sensing, quantum networking. So, studies have been performed in the different research institutions worldwide to explore the utility of QIS, quantum sensing, in the area including the high energy physics, nuclear science, and in the quantum chemistry, economics, communication and optimization. As we know that the quantum technology has a various field where we are working, like in the communication, like in the computing, like in the material, like in the sensing, and now the further QIS is expected to be particularly useful for the energy sector also. So, energy stage proposal seeking applications are being investigated in the research institution around the globe in areas such that the nuclear energy, material science and energy infrastructure optimization. So, QIS, quantum information system or quantum technology, further just working in the energy sector also. So, quantum sensors for the energy applications have the various applications, like it is having a growing investment into the quantum sensing based research that will create the opportunity for the quantum sensor deployment in the range of the energy relevant application. So, there are the several exciting area of the application, which includes the renewable energy, nuclear energy and nuclear waste management. That is also the very important part. So, this quantum technology is working in the field of quantum energy, where we are having the management of the nuclear waste. So, management of the fossil energy, management of the geothermal energy, electricity delivery and the reliability. that is also having in the vehicle electrification. So we can use the quantum technology in the vehicle electrification. Nowadays we are using the EV cars, vehicles. So in EV vehicles, so quantum energy can be work in an efficient manner for the vehicle electrification. And the energy efficiency, that is the most important part nowadays, how we store the energy and how we use the energy in an efficient manner. So this quantum technology will work in this energy field also. So common themes can be identified that span many of these various areas of the applications, that include the monitoring of the energy infrastructure, advanced manufacturing, electricity delivery, transmission, distribution, storage, building energy efficiently, and fourth is the nuclear. If we talk about the monitoring of the energy infrastructure and advanced manufacturing, it contains all the reservoir where we are having the energy from it may be getting from the various sources. So that monitoring can be done through the quantum sensors. Moreover, electricity delivery, transmission, distribution and storage, that is the most important part of the energy storage, where we talk about the batteries, we talk about the supercapacitors, we talk about the charging, discharging, efficiently charging, discharging, stability of the battery, stability of the energy storage, and we talk about the energy storage devices. So we use the electricity storage, in which moreover it is very important when we store the energy, how we transmit this energy, how we redistribute this energy for the various purposes in the efficient manner. So electricity delivery means electricity delivery and transmission, where we use this stored energy in the various sectors so that it can work efficiently. Another is a building energy efficiency, means how efficiently we can store the energy or we can get the energy. Like if we talk about the supercapacitor, there is a charging, discharging. But here what we want nowadays, as we are talking about the quantum technology, we use the fast charging as well as the slow discharging. So that and fast charging means we use the sensors in such a manner so that it can, we use the quantum batteries in such a manner so that it can charge in a faster manner. So faster charging is important in the quantum technology. Another is the nuclear energy, how efficiently we use the nuclear energy. The first is detection of the nuclear particles is very important. To the quantum sensors we can detect the nuclear particles and how we extract these nuclear particles. After that, the storage of the nuclear particle, then after storage, then how we will use this nuclear energy in a efficient manner, so without damage the system or without damage. So it is a very important in the quantum technology, which is working on the quantum batteries, we are working quantum storage devices, which is working on the quantum energy efficiency. So this field is further discussed in the next lecture, where we discuss the various types of the quantum batteries. We have discussed about the energy storage processes, how we can efficiently use the renewable energy, how we use the fast charging or discharge or slow discharging devices. So there are several exciting areas of this energy applications where we need to work, and we just to store the energy or we use the and transmission of the energy. Moreover, we can efficiently distribution of the energy can done. So there are the various field where we can use this energy storage, and if we talk about the any sensor, so we can use this sensor so that it can work for a lifetime, for a lifespan. Similarly, just in the quantum batteries, the researcher are working so that these batteries can work in a full lifespan, and there is no need to charge this battery, but once it is charged, it is just having a very slow discharging or dissipation so that it can be used for the lifelong. So there are the various quantum energy applications, where we create the opportunity for the quantum sensor deployment in the range of energy relevant application, from the detection to the storage to the transmission. So we have the various energy storage devices as well. So in the next lecture we discuss the quantum batteries, that how the quantum batteries are prepared, how they use the quantum technology, and how we use the quantum batteries in the various quantum applications. So further this node we can just discuss the quantum batteries applications as well as the preparation of the quantum batteries, and moreover we discuss the quantum energy storage devices, how efficiently it will work, how we can calculate its efficiency so that it can be used in the various application of the quantum field as it is a growing. So from this node we are very much thank you very much.